Yeah, it's great.
Perfect. All right, back from commercial break. Today's lesson is sponsored by the letter B. Kind of like Sesame Street? You kids are too young for Sesame Street.
Yeah.
Now, it's an old classic show. You know, check it out sometime. People used to get that. Okay. All right. Now, find the intervals of increase for the graph of this. All right. So we got this graph, and I want to find the intervals of increase. Now, again, let's make the connection. If a graph is increasing, what have we learned recently?
Slope increases.
Okay, your slope is definitely positive, right? Tangent line slope is positive. Okay? Therefore, all I have to do is find out where the derivative is positive. Of course, I'll have to find the neutrals first, right? Okay? If you can find where the derivative is positive, you will know where the tangent lines are positive, hence the function increasing. All right? So I want you to remember this from this day forward. All right? All the way through to the very end of AP Calculus, actually, in any college calculus class that you have. If you see the word increase or if you see the word decrease, immediately think derivative. Okay? This will be true. All right? So let's take the derivative of this. And how shall we take the derivative of this?
Move it to the top.
Yeah, let's not take the derivative yet. I guess you could do the quotient rule. It would work. I'd rather do the chain rule. Make that -2. All right. So the derivative will be -2 to the front. Inside stays the same. New power, -3. Chain rule times 1. So the derivative is officially -2 over x minus 3 quantity cubed. All right. So far, so good. Okay. And that's my derivative. Now remember, I want to find where it's increasing, so I want to figure out where the derivative is positive. Well, don't do this. You can't solve that. Where does it equal plus sign? Infinite places. All right? So remember, before you find the pluses and the minuses, what do you have to find first? Okay, find the zeros, right? Okay. Matter of fact, I tell you what, let's label this today, since we're going to have 2 cases today. Let's label this case 1. All right? Case 1, find the neutrals like we did in the homework last night. Okay, so where does that equal 0? Let's see here. Yeah, there's a problem here. What's the only time that a fraction ever equals 0?
It's on top.
If 0 is on the top. Not the bottom, because that does not exist, right? If there's a 0 over anything, you get 0. I don't believe -2 could ever equal 0, could it? Okay, so we don't even have any, what are those called again?
Neutral point.
Okay, neutral points also known as? Okay, critical numbers, right? Okay, same old critical numbers again. There are no critical numbers in this problem, right? Well, I guess I'll just give up then. I'll just throw my hands up. Okay, all right. Okay, no solution. Next, wait a second, there's a solution here, but there are no critical numbers. All right, now here's the scoop. We are going to draw a, what's called a what? Number line, otherwise known as a first derivative test. Yes, I have to do a first derivative test. Okay, you can ask the kids in calculus. They're getting to the end of the year now. They're still doing first derivative tests, just with more complex problems. But it's that useful. Okay, this will cover you for years in math. Okay, so first derivative test. Now, on that first derivative test, do you remember the goal that I mentioned during the homework? We have to plot everything that is not what? Not. Okay, we have, some of them are neutrals, but they're not what? They're not negative, and they're not positive. Exactly. You have to make a number line slash for everything that is not positive and not negative. So that when you get to your sample points are only pluses and minuses, as they should be. Okay? But if you want to make sure that your random sample point you choose is plus or minus, you better mark all the things that are not plus or minus. Okay? All right. So critical numbers, we don't have them. But isn't there something else other than 0 that is not plus and not minus? Something else is not plus and not minus. Does not exist is not positive and not negative. Only 2 things in all the world of mathematics that are not plus and not minus. 0 and doesn't exist. Okay? So you can't just look for the zeros today. You have to do today case 2. Find where the derivative does not exist. It's not a critical number, but it's just as important. Okay? Let's just say B and E there. All right, so let's figure out where this function does not exist. Wonder where that is. To get does not exist, you need a zero where? In the denominator. Okay, can you plug a number in there that would cause us to beat D and E? What about x equals 3? If you plug in x equals 3, the derivative does not exist, and that is not positive, not negative, so we better plot that. It's just as important. Okay? Now don't worry, you won't get to calculus and have 17 cases. They still have 2 cases every time they do this. Okay? And we do it like weekly at least. All right? So there are only 2 cases, that's it. All right? So look for your zeros, look for your D and E's. Why did we not have to look for the does not exist for the derivative on the entire homework? What was not on the homework? Okay, we did not have a denominator, and even if we did have a denominator, there was not a variable in the denominator, because if there is, you have to worry about the D and E case. That's the only difference today. Okay, think about the D and E case. All right, so no critical numbers, but boy, if you don't plot that 3 over there, you're not going to get the right answer for this at all. You've got to look for the does not exist. Okay, matter of fact, I even note, remember we did m equals 0 a second ago? So this, I'm going to note that that's where the derivative does not exist. Okay, because that means something different that we'll go into later. All right, now I can go about plugging in my sample points, and I won't worry that I accidentally pick 3 and stumble upon this does not exist and get confused, because I have marked the only thing that is not plus and not minus. Any other number in the world plugged into this derivative, and you either plus or minus. Okay, so what do you want to pick below 3?
0.
Let's pick 0. Okay, how about above 3?
1.
All right,
1,000.
how about, okay, 1,000, I'll take 1,000. Okay, sure. All right, now, plug it into the official derivative. Okay, if I put in 0, 0 minus 3 is negative 3. Negative 3 cubed is a what? It is definitely a negative, right? And negative 2 on top is always what? Always negative, no matter what you plug in for x. A negative over a negative is a positive. And it doesn't matter if you plug in 2.99 or if you plug in negative a billion, you're going to get a minus over minus is a plus. Okay? So we can all agree no matter what point you pick. All right, 1,000. What about 1,000 take away 3? Positive minus negative 7, yeah. Cube it, and you get a big old positive number on the bottom, but a negative on the top. So you get a negative over a positive is a negative. Okay? All right. That tells me that the original function is what and then what? F is, yeah, positive slope, so it's doing what?
Increasing.
F is increasing, and F is decreasing. Okay? And some of you, if you thought about it, you already know what this looks like right here. And it makes sense to you. You know what this is? It's 1 over x squared, essentially. It's a hyperbola. And if it's x to an even, are they together or diagonal?
Yes,
Together. And if it's positive 1, is it up or upside down?
Up.
Like this. Okay? Does that match the information? Wouldn't that be increasing and then doesn't even exist and then decreasing? Doesn't that make sense? Okay? But it's not an up-down peak, though. It's an up and then down that step. Okay? So in other words, does not exist can separate the worlds of increase, decrease, just like a 0 can. Okay? And so the final answer for, we're looking for increase, so it is increasing from where to where?
Negative
Infinity up to, but not including that 3, right? Okay. All right, Tim.
If the original function, like, if you look at the numerator for the original function, you determine whether it's above the x-axis or below.
Yep.
And then you look at the derivative and that's negative. If the derivative measures slope, then why do you look at the original function?
Well, you could do it, as a shortcut too. If you know what the graph looks like, you can, when you do the first derivative test, it reinforces what you already know, essentially. So we know for sure that this function has to be increasing, therefore its slopes are positive, right? Okay, it's the only tangent slopes. We know that it is decreasing, so all the slopes have to be negative. And then we know right here, down the middle, if the function doesn't exist, then the derivative will never exist. That's always the case, regardless, okay? And again, if you know what it looks like, you can kind of sketch it instead, but a lot of these will have no clue what they look like at all, so you'll only be relying on the first derivative test. That's all you have, okay? So in those cases, you pretty much have to do it, okay? But it should match the information that we know from this right here, okay? So in other words, we're not looking for above and below the x-axis today, like we were in the first lesson. We're looking for steepness, is what we're doing today, okay? All the steepnesses are going up. Steepness doesn't even exist. All the steepnesses are going down. Okay? So think slope. Don't think location above and below, but think slope, in other words. Okay? What is the slope? All right? Now, if we had done an original y-test on that's what we did in 10-1, right? If we just did a y-test, the original function test, we would have gotten above plus and above plus. That's the y-test, not the y-prime test. Okay? All right, now, the last case is a very special case. One of my personal favorite problems.
5 minutes.
And that's no problem. That's all we need.
Probably 10 seconds.
It's like my director off stage back there, speaking into my earpiece. You get 5 minutes, wait. Wrap it up. All right, so for this one, all right, let's take a derivative. Now, of course, again, I'm going to rewrite this as 2x minus 1 to the what?
Negative.
2. All right, what is the derivative of 27 halves x?
47 halves.
27 halves, right? Okay, I'll take that as 27 halves. All right, if you take the negative 2 times 2, you get negative 4 x minus 1 to the third. Chain rule? 1. So here is your official derivative. And you know what? By now, you kids know how to take every derivative known to man, almost. Okay, except for a few out there. You got all the good ones. So you know how to do this. All right, here's your derivative. Now, first things first. What did we do on the homework, and what would you always want to do?
Find what equals 0.
Case 1, find your neutrals, right? Otherwise known as critical numbers. Okay, so set it equal to 0, all right? Oh, but Mr. Wade, 4 can't be 0, so certainly this won't.